Hi guys, let's look at something a bit different on this video. So this is a battery charger, lithium ion CPC charger thingy, okay? I don't have the batteries that it charges, he just brought me the charger. But what I do know is if I connect the power, nothing happens. So one would assume, yeah, see where that gets us. One would assume this light would light up when there's power on and then flash, I'm guessing, when it's too hot. That's about the best I can come out of that one. There's no on off switch or anything daft like that, so looks like, yeah, these come out and then there's some screws, torque screws. Okay, so it shouldn't be too difficult to get into this thing. Well, yes, it comes apart easily. Okay. Oh, quite a hefty switch mode power supply in here, actually. That's what we have. Looks like, yeah, the big thick wires must be the power up to there. This must be some sort of sensing. Mains in, there's a fuse, filters, bridge rectifier. Could be another filter. This could have PFC on it. I don't think it's got PFC because there's the bridge rectifier is there, and then there's the two switching devices, but one could be PFC, one could be for the transformer. Rectifier diodes on the output capacitors. We have a small transformer as well as a big one. This might have some sort of drive coming from this side driving those. We see two opto-isolators by the looks of it under this gunk, so probably one is regulating the voltage. Yeah, the other one maybe switching the PFC. It's a bit hard to say just looking at this side, but we have a transformer as well. We have both. Okay. Unless this has some sort of standby supply, that's another possible. Just looking at it so far. Let's do a few basic checks. And then we'll start to figure out A, what's wrong with it, and B, what we need to learn about it. Question number one, has the fuse gone? Was switched off, I've unplugged it as well. It was switched off at the mains. Has the fuse gone? No, the fuse is good. Okay, second question, is there any voltage coming out of it? Switch it on. False. Negative, positive. No, there's no voltage coming out of it. Okay. Could be a nasty charge in there though. Yeah, could be a nasty charge in here. Well, to get any further, I need to unscrew this PCB. I can see the fittings. I can't get behind it to see if there's any voltage in it or not. That makes life a bit more difficult. I can't even easily get to the legs of the bridge rectifier to do that because they kind of like insulated behind these things. And anyway, if this has PFC, that's another device down there, which makes me think it does have PFC, then I wouldn't see any voltage across the bridge rectifier even if that was fully charged. There's a chip there, just noticed under here. I think that is probably some sort of standby supply. And another one here, that's a chip in there as well. You can see them now more clearly. This is kind of like rubbery type stuff, so it'll probably come off not too difficult to get off, I think. Okay. I think the best bet is to just carefully unscrew this and lift it up so we can check if there's any voltage in this. I can also remove these as well. I don't need these on now, if they'll come off easily. Okay, so it lifts out, yeah, safely. Let's see if this was going to electrocute us. Okay, so large capacitor is here. Okay, and it doesn't have any voltage in, or not now at least. Okay, yeah, nothing in that. Oh, there is. Look, see, I had a bad connection. This is what you got to be careful of. I just had a bad connection. It has over 140 volts in it still. I use this to discharge these capacitors. So this is a 2.7k, I think, 5 watt resistor. This won't make sparks or do anything. It will just discharge it if we get a good connection against it. We can soon check because we can measure the voltage again. 121. So I'm probably not getting a very good connection actually trying to use that to discharge it. I'm just looking at this as well. So Hilti C436-350. I did a quick Google search to see if there's a user manual for this, and actually there is. So what I was interested to know is whether this LED should light up when there isn't a battery on here. And Google says it should. So this is the user manual. It says here display. So this is the LEDs on the battery. This is on the charger. So LED doesn't light, charger malfunction. Okay. Or if the green LED on the charger lights, but there's no lights on the battery, then it's a battery malfunction. So it doesn't light up. So that would say this does have a charger malfunction. Mine is this model, so up to 36 volt. Okay, 360 watt. You can see the ratings here. Operation: plug the supply cord into the power outlet of the green LED on the charger light. So this should light up, yeah, without a battery attached. It then tells you how to replace the battery. Troubleshooting, this will be useful, yeah. LED on the charger doesn't light. Possible cause: charger malfunction. Action to be taken: unplug it, plug it back in. Oh, switch it off and back on again. If that doesn't work, bring it to Hilti service. Yeah, I think we'll have a look instead. I think we'll ignore that. Yeah, there's probably no user serviceable parts inside, of course. Yeah, so that's the charger. First thing then is, where is the controller for the switch mode power supply? And there's one there, so that's probably it. It's directly underneath here. That's what you'd expect it to be. This clearly is the high voltage side. You see there's a mark down here, so this is the high voltage side, this is the low voltage side. So crossing the divide, if you like, we have some opto-isolators here. We have another opto-isolator there. Okay, and then we will have the actual transformers. So this is your main transformer here, again crossing that divide, and the smaller transformer, which is that one, yes, that also crosses over this divide, primary, secondary. So this looks like it's probably a standby supply. Okay, now let's have a look at this chip. Let's see if we can find a data sheet, and then we can kind of go from there, I think. And we can see L6599AD, okay, which is this device. So there's the chip. We can see switching to MOSFETs. It shows a optional pre-regulator. So this is PFC. I don't know if we have this or not, but we need to figure out. You'll see we have one large capacitor here, the two switches. So we can see how the primary is wired up via a high voltage capacitor, primary to hot ground. Okay, so we can see basically how this would be connected up, and then a center tap to secondary, generating the output voltage. We also have a typical application here, so this gives us a probably very good idea of how this is set up. It's kind of sideways, but I think you can see that is the controller switching the transformer. This is the PFC chip. Yeah, so this is your PFC circuit here. You can see that. That's your PFC MOSFET. These are your main power supply MOSFETs. You can see there's an auxiliary winding here, so this will be feeding power, yes, like through a diode, a capacitor, back into our circuit. So that actually powers, by the loop, sorry, yes, the PFC chip and this chip. Just zoom in a little bit, we can see it a bit closer. So power's coming in here. Yes, now we've zoomed in a little bit more, we can see through a rectifier diode, capacitor, then we come up here through another diode, and then this has, on this application, a transistor wired as an emitter follower, a Zener diode. So this will give a fixed voltage on the emitter via a diode that powers the PFC chip, and if we look, it also powers our chip on pin 12. So that's where our chip should be powered up. But of course, the power supply has to be running before we get a voltage here, so it needs a startup supply. No, actually, it looks like the startup supply comes here. So we have these 2.2 meg resistors in series. We have some 1 meg resistors in series. These ones power the PFC controller, and these ones then form a voltage divider here. That's also going into here, yeah, and it's also going via this resistor divider, another resistor, capacitor to ground. Yeah, this one line. So pin 7 looks like the startup supply. I'm fairly convinced our circuit will be something similar to that. So we know that. Now the next thing I want to just work out is whether we have PFC on our charger, because it says that is optional. Now that's easy to work out. So you can see here the bridge rectifier. So this is your power coming in, okay? And with PFC, that goes via an inductor or a transformer like this, via a diode, an NTC, and then this is your large smoothing capacitor here, yeah? That's the MOSFET switching this end of the coil. So if we measure from the output of the bridge rectifier to the positive end of the large smoothing capacitor, if we just see a direct connection, then we don't have this PFC. If we see a diode, then we do. If we just go back to the top of the data sheet, this is possibly more clear here. But yeah, it's probably a little bit clearer here in this basic system block diagram. So you can see this is where the positive of the bridge rectifier is, negative, which is hot ground. And if we have the PFC circuit, then from here to the large 400 volt capacitor, we will see a diode. If we don't, there'll be a direct connection. Here is the pinout. So 12 we know is VCC. 7 is where we think the startup supply comes in. Oh, it says this is a line sensing, so maybe this isn't the startup. So looking at this again, we know that the secondary here provides the current for the chip to keep running, but it needs a startup supply, and that looks like what this is doing. So bear in mind we have like a pulsed DC here at about 100 Hertz, because that diode effectively is disconnecting the bridge rectifier here from the capacitor, okay, the large capacitor. So even when the PFC isn't switching, here we have like pulses, Okay, other side of the diode is the smoothed DC. So this acts like a transformer. Look, we can see 10 ohm then through a capacitor, so that passes the AC. We have a couple of diodes, and that comes back to the base here. So that's going to put a voltage on the Zener diode. But imagine the power supply isn't running yet. There's no supply coming from here. Okay. The collector of this transistor will have no supply on, but the base will be above the emitter. So base current will flow. Yeah. Base is more than the emitter, so the current will flow through that junction, even though this has no supply. And that takes us to these capacitors. So that's how I can see this gets its startup supply via this. And obviously once it starts running, it then gets its auxiliary supply via this diode to the collector. Now, if ours doesn't have PFC, it won't have that type of arrangement. It'll probably have some sort of high voltage resistors in series to provide the startup. Okay, so we know something about that. Now let's figure out if our power supply has PFC or not. From the data sheet then for the controller, we know some other things. We know that 2 of these devices, and there are 3 on the heatsink, 2 of them are the switching MOSFETs for the LLC circuit. We know that now. We know we have 2, even though there's 1 capacitor. And the other one, probably this one, these are probably the switches. The other one is something else, okay? Could be PFC. I thought he said PFC there, but he actually says PC, okay? So let's see. Do we have PFC? This is the positive end of the bridge rectifier. We can see that. It has a chamfered edge here. This is always the positive side. So this is the positive leg of the bridge rectifier. And then the main capacitor, which is there. So this is the positive end of this. Let's get into shot for you there. Do we have a connection? Well, let's just go on to diode mode. So we should see either a connection or a diode. And we don't see anything. Okay. Don't see anything. It won't be this way round. Well, you'd think that might be the fault on this, but we know that's charging up, so there must be a connection. Yeah, I mean, we know the capacitor charges up to a rather nasty voltage. Let's track it through. So, negative end of the bridge, negative end of the cap. That's hot ground, okay? That's fine. So the positive end doesn't go. Goes here. Oh, look, at this thing here. So it goes to here. Is this a MOSFET? This is that other device on the heatsink. And then out from here. Oh. So that device is connecting the power from the bridge rectifier positive to the capacitor. This thing here. That one, okay. Looks like a MOSFET. Well, if that's a MOSFET, then this should be the gate drain source, you would think, or gate source drain. Okay. And this appears to go to there. What about this one? Oh, that also goes there by a resistor, low value. So there's a low value resistor. Okay, 59 ohms. This might not be a MOSFET. This might be something like a triac or a thyristor. But if the voltage is getting to there, and we know it is, that must be switched on. Fortunately, the adhesive on this is quite soft. It's fairly easy to remove. This gunky stuff is kind of like rubbery in texture. So We can see that that device is BTA12. We should be able to find a datasheet from that. Maybe that will tell us a little bit more. And it is a triac. You can see it there. BTA12, suitable for AC switching operations, can be used as an on-off function in applications such as static relays, heating regulation, blah de blah. Okay, so one reason I thought this might be a triac is because it looked like the gate was connecting to the output and it didn't make a lot of sense. And I do know that with triacs and thyristors, often the gate is on this end, a different layout you would expect to a MOSFET. Okay. It seems there are a few manufacturers of this because mine is an ST one. Okay, ST, we have it there. But it's the same thing. So that is a triac, okay? So something on here can switch that on or off, which tells me straight away there must be a standby supply. Yeah, because the something that can switch that on or off needs to be powered up when that is off. Yeah. There's also a large inductor or transformer here. This could be a PFC, but you don't normally, well, you wouldn't use a triac in a PFC circuit, so maybe that is not at all. Plus, the output of that goes directly to the capacitor. I'd say no. There's a, what's this thing down here close to it? Oh, MOC 3063. That is a opto-isolator, okay? MOC, I know these quite well. There's a few different models. 6-pin opto-isolators. Probably don't need to get that gunk off. We can just look on the other side. So it's just the other side of the triac, which is there. Yeah, so there's an opto-isolator here. That's driving the triac quite possibly, but it's not driving it from the low voltage side. It's still on the high voltage side here. All this is high voltage circuitry, but something here is, it looks to me, driving the triac. This we know is the gate. Yeah, look, there's a 100 ohm resistor to here by the looks of it. Yeah, so we can say that the opto-isolator is what switches that on. Whatever controls the opto-isolator is on the high voltage side by the looks of it. But you won't have a high voltage side until it's switched on, so something is obviously starting this up. Let's see. This is the low voltage side. This, then, I would say, is a standby supply. In fact, there's a chip down there. What's that thing? MIP2M2. It's right next to the transformer, so I'm pretty sure that is a little switch mode controller, basically. Looks like it has 7 pins as well, like a missing one there, which you would expect if this was the high voltage pin here. Okay, let's find a datasheet for that one. MIP2M2. What's a 2M4? Do you know it doesn't actually find it? It's found something similar. Some sort of power supply thing, yeah. MOSFET, drain, source. So it's not the same one, but that is, well, it says it's a MOSFET type integrated circuit, but it looks like some sort of pulse width modulator to me. Basically, like feedback, source, drain, yeah. How can we go about this then? I mean, from what I can see, we have power getting into here. If we measure the voltage on here, by the way, and it's more than 320, we do have PFC and it is running, although I think we don't have PFC. I do think this is switching on, so something in here is switching that on. But the microcontroller is over here. This is the low voltage side, Possibly something on this side of the circuit is controlling that. And you would expect it, because this is where the brains is, basically. We have 1, 2, 3 opto-isolators here. Okay, so one is going to be feedback, and we have 2 more. So one of these could be the signal to turn the triac on, and then the triac itself is actually turned on via yet another opto-isolator. That may well be because the gate voltage on here is effectively at mains potential, and this circuitry around here, which is switching it, is at a lower potential. But that's not giving isolation, mains isolation. So both the LED side and the transistor side will be connected to hot ground. This will all be on hot ground, and we would then have another isolator, one of these two, so this can control that. Yeah, so 2 opto-isolators, don't see any reason why it can't be that way. There is a third one. Maybe one also switches this on or off. This has some sort of enable pin as well. Let's see. So I think the first thing we want to figure out on here, or the first 2 things, is what voltage is in this large capacitor when it's switched on. Okay, is it 320? Is it about 380? And the second thing is, do we have a supply coming out of this, which is obviously a standby supply. Looks like the capacitor on the output there may have more than 1 voltage rail, may have 2. Let's see if we can just figure that out. Well, here's our transformer, and we can see that these 2 pins are in parallel and those are in parallel, so it looks like a single voltage output going to this diode here, and then we have a capacitor. Okay, so I would say this is where we're going to find the standby voltage, and this will be referenced to safety ground. So just a quick check, this is the diode, should read like a diode. Yes, it does. Okay, so we know where that is. Then ground, you would assume, is here. Other end of the secondary would make sense. In fact, it goes to the negative end of the capacitor as well, so that must be ground. So we know where to take some voltage measurements. Right, let's get on to it. One other thing I'm sure we can say as well is that this isn't running, because when we switch off, the main capacitor stays charged up, this one, with a very high voltage. Okay, power on. What's in the big capacitor? $309, so there's no PFC on this, or it isn't running if there is. What's on the standby supply? So that's here to here, minus a very little amount. Okay, so it looks like the standby isn't running. This we think is ground. Yeah, minus 0.12. So I would say the first problem with this is the standby supply isn't running, and if there's no standby, then nothing else can work. That triac, by the way, could well be that turns on by default. Okay, and this can switch it off rather than switch it on. That would explain why we get high voltage in the capacitor here. I think another good reason, by the way, that we can say the standby isn't running is because if it was, it would be draining the large capacitor. And we still have, well, 257. So it is draining, but it's draining very slowly. I'm sure if the standby was running, that would be draining much faster than that. Guys, while I was waiting for these capacitors to discharge, or rather this one big one, I got nothing else better to do, so I finally made myself a little discharger out of a couple of old meter leads, basically. They're not the best, they have these ends on, but they'll fit into any meter, I guess. a little bit of heat shrink. This is my 3K3 5 watt resistor, and normally, you know, I hold this against the capacitor, but I noticed with this board it was a bit difficult because of this lacquer coating on it. So what I can do is now I can just connect this to a multimeter on volts range. Okay, and I can now just discharge the capacitor like this. So this is a lot safer, to be quite honest, than the way I was doing it. And we can also see whether it's discharged. There's probably still quite a bit of voltage in this. Let's have a look. So it was almost gone, but look there. I now have a nice safe capacitor discharger. Yeah. Of course, I have to remember to only use this lead for that, although I guess if I try and measure a voltage with a 3K3 resistor on, it's not really going to blow too many things up. But yeah, I have that. In fact, I have here just a spare multimeter. I don't use this. I think we got this just to play around with on the live stream, just to see how the chip meter was. In fact, no, I'll tell you what, actually, it's on my channel. So if I just leave the leads on that, this is now my capacitor discharger. I can just grab it whenever I want. I think that's quite handy. All the evidence then is telling us that this isn't running. Now, that could be a faulty chip. I can check for short circuits on the output to make sure it isn't that. The problem is I don't have a data sheet for this. I'm going to have another look, see if I can find one. Can I even buy these things? It would be nice if I could find a data sheet, because then I can check to see whether this has, for example, a startup voltage. Yeah, okay. Well, we know the output is here, so we'll measure across the capacitor. No, we have about 500 kilo ohms there, 400 kilo ohms. So there's no short on the output. We know the diode measure's good. So you would expect, unless the transformer itself is faulty, that the problem is with the chip or the circuitry around the chip. I can see the chip then. So this is the high voltage pin because there's a gap there. Okay, so that's to isolate or keep the high voltage away from the low voltage to stop it arcing over, and probably to meet certain safety regulations. So that's the high voltage pin. We can see that goes here to the transformer. So there's 1, 2, 3, 4 pins here. That's the secondary we've been looking at. So that goes to there. So yeah, it's going to be this one, the other end of the primary. This should go to the positive end of the large capacitor, which is here, but it doesn't. Yeah, I would have thought that would have gone there. And then obviously ground on here will go to the negative end, so that you would expect to be a ground pin. Probably that one and maybe this one as well. Okay, just that one. Yeah, so this effectively is your MOSFET inside here. That goes to ground. And then the other winding is going to be the auxiliary, which is the supply that keeps us running. So this would go to hot ground, which it does. And then I can see, yeah, a diode there. And that will supply, there'll probably be a capacitor somewhere here. Probably one of these SMDs. Yeah, that goes to this, which looks like it's VCC. And that may have some sort of startup supply possibly coming through this other diode off over that way, some high value resistor. It's heading in that direction. This one. Yeah, and that's heading off. Does that go up to the... via something or other? Yes. A high value resistor, you can see there, yeah. You'd expect that to be a high value resistance. I think that's the startup supply coming in, because that also goes to here, I think. Yes. And this is the main supply from the auxiliary winding. What I can't figure out is how this here gets its supply voltage. Something should be supplying that with a high voltage. Do we have something open circuit in here? This looks like, well, is that a Z diode? It says ZD. I'd expect this to be reverse bias, so this will be, go to diode mode again. This is probably the flyback diode, I would think. Positive enter here, or rather the anode to here. Okay, where's this thing go? Well, obviously we know it doesn't go there. What is that thing? That looks like it's one end of this transformer. I had another look for a data sheet. I can't find the exact one. I think this is very similar. So we can see we have the drain on pin 5. That matches what we have. Pin 6 is missing. 7 is the source. And I think this is like a current sense type pin as well. But that again matches what we have. VDD, this is power coming in. So I think this again matches what we have. There's also a VCC supply pin as well. You can see the drain here. So this has a current source built in. Can you see this funny little symbol? Like 2 Olympic rings. This is a current source. It has a soft start. So that is how it gets the initial power to start up from here. And then the auxiliary winding takes over and powers the chip to keep it running. So this looks very much like what we have. We can see in the various specifications, drain voltage up to 700 volts. So that is the high voltage pin coming into our chip. This is how the circuit should be then. We have the chip, pin 5 is the drain, this is the source. Okay, so the source goes down to hot ground. The drain will go to the standby supply transformer, and this will go to the high voltage HT plus, which is basically where our large electrolytic capacitor is. Other end of that to hot ground, and then of course we have the secondaries. There's a secondary on the low voltage side, and we have another secondary on this side. I didn't really leave space to draw it, but the other secondary connects to hot ground. It has a winding here, and then this goes through a diode, and it feeds the power back into our chip. Okay, and there'll be a capacitor here as well, probably a little surface mount one to hot ground. So that's what effectively we should see. We should be able to find one end of this winding going to hot ground, one going to a diode, and there may be, as I mentioned before, a startup supply, so another diode coming in here via some resistors up to here. But I think, according to the data sheet, if it matches ours, that startup voltage is actually generated internally in the chip. That was that funny little symbol we saw. Okay, like that. So that's what we have. And what I can't find is how this connects to their HT voltage plus. Okay, I can't find that connection at the moment. All the evidence then tells us we should have a high voltage on here, and the high voltage must come from the large capacitor, and we don't have a connection there, 7 mega ohms or something like that, and there shouldn't be really any resistor in between. There should be like a direct feed into here via the transformer winding. So we know the transformer winding, we've already seen it, there to there. Okay, what we should also have, because we've seen the other data sheet, is the HT plus effectively goes to 2 MOSFETs. This is your main supply, wired in series like this. Okay, that again will connect to hot ground, and this is where we have our coil, high voltage capacitor, also connecting to hot ground, okay? And obviously the L6955 chip, I think it was, is what's driving those, okay? So that's that one. So that's what we should have. Knowing that about the circuit, if we go from the large capacitor, hot ground plus HT, okay? So we know this is the standby transformer. We see 4 pins here. These two connect together. I think I'm just seeing the resistance of the actual coil there. Okay, small resistance of the coil. They don't connect to these two. These two connect together, and we had a look. We know this is where we have the diode coming in from the winding, this one, feeding power back into our chip. Okay, so we know that. From the other end of this winding then, this is where we would expect to go to the positive of here. It doesn't, right? Nor does it go to hot ground, where we would not expect it to go. But we do know that the other winding, this little secondary, this end goes to hot ground, and that's how we drew that little schematic out, roughly how it's connected. So that is the auxiliary winding, this is the primary winding. The winding itself is okay, but I don't have a connection from here to here. Okay, now the large transformer, you can see the windings are here. The MOSFETs are here, so we have one there, 3 pins. We have another one there, 3 pins, okay. So we know these are connected in series. If we go from plus HT here, it will go to one of the drains, not that one. That one, okay. And then the source of this one will go to the drain of the other. Just find the right pin. Yeah, that one. Source to drain, and then source of this one will go back to hot ground. There, okay. So we have that path all the way through. Drain, source drain, source to hot ground. So there should be a connection from here to here, and I don't see one. Now this looks like one end of the transformer winding. These are the other windings on the primary. We can see that this is the secondary. We can pretty much say that because if we look at that point, and there's a hole here, a mounting hole. The mounting hole is there, so there's a pin on this corner of the transformer here, which is that one, and that should connect to one of these somewhere. Doesn't go to anywhere. That's a winding from there to there. There's another winding from there to there. They're not connected to each other. One of these will be an auxiliary winding, generating the power to that. Okay. One will be the primary, which will connect to the junction of the 2 MOSFETs. There, that's the junction. So this you would expect to go to one of the windings. Yep, goes to there. The other end of that winding will go to the high voltage capacitor. Looks like it's this one. And then from here to hot ground. So all that checks okay. What we seem to have is an open circuit, possibly in this winding. It does seem rather odd though that the HT would get to here via a winding on this transformer. Maybe this is just like a physical mounting point for it. In actual fact, and doesn't connect it anywhere on the transformer. It certainly doesn't go to any of those pins. We have some resistors around here. Let's have a look what we have. So Oh, that looks a bit suspect maybe. We have, this is a 10 ohm resistor. So that connects to there. And that goes to there, 10 ohms. And it looks like it goes through this one, so it'll be 20 ohms. Yeah, 20 ohms. And then it comes this way via what looks like a 1 ohm, which reads open circuit. That then goes off up here somewhere. What's this one? Well, that also reads open circuit, and then from here to here, is that a connection? Yes. That also reads about 19 mega ohms. This goes to here. Does this go to the high voltage here? Yes. So that's the path for the current to this chip. Yeah, top end of here through some low value resistors. And they look like they're gone. Let's see. I'll get the microscope, see if we can read what they are. This one first, and this actually looks physically damaged a little bit. Hard to read the marking on that one. They've got to be low value resistors. That one I think is 1R00. This one I think we can see is 1R00. Let's try clean some of the gunge off them. Well, with some of the isopropyl alcohol on here, I think it actually shows clearer. That one, the last one, that's R7. I think we can fairly clearly say that is a 1R00. And they're going to be the same in series, I'm sure. So we have 1, 2, 3 1 ohm resistors in series, which feeds the power down to here. Now, those resistors will not just fail. They will fail for a reason when they fail like that. And that's too much current went down here, okay? Let's have a look at the chip. What do we read across here? Do we read anything? Well, it reads into the mega ohms. Okay, there. But I'm fairly sure that chip will be blown. I don't see why these would fail. You can see like there's a hole in that one. And in that one. Yeah, they've all got holes in them, so that's failed because of too much current. We need to replace this chip, and we need to replace those 3 resistors, and then we might have a good chance of fixing this one. Well, in fact, I can get these. Actually, this particular seller, SUHMS, Zooms, or whatever they call themselves, I've used these a lot in the past. If I see them, they tend to be pretty much the same price. Shenzhen, Hongming Electronics, those ones, yeah, those people. So these have been reliable in the past. I prefer to buy from these if I see them. We can get 5 of these for €2.94 plus another $1.18 and postage. That's an attractive price anyway. So those can go in the cart. The 1 ohm resistors I will have, but honestly guys, unless you want to chastise me over this and call me a wuss, there's no point as far as I see changing those resistors unless I change this at the same time. Well, there we have it. This is what I would call a good, honest fault. We found a very good reason why it's not working. I think we found that, if you like, the collateral damage, those resistors. Although I can't really test the chip, I think I have very good reason to expect it is faulty, and they're cheap to buy them. Probably this is why the fuse didn't blow, because those resistors blew first. That seems to be the case to me. And I think we've got a very high expectation of this working once the parts arrive. And if it doesn't, well, you'll just see it again. But I think this probably will work once I've changed those. So I hope you enjoyed watching that. I hope maybe you've learned something as well. Maybe you'd like to talk down there about the way I actually diagnose this. I mean, do bear in mind, by the way, I'm actually trying to teach the technique, so I'm not always doing this the most straightforward way. I'm just trying to do this in the explanation of how you should go about it. But guys, if you think it should be done differently, you know where to talk. Yeah, let's chat. So that's about it for this one, I think. I look forward to seeing you all again soon on Learning Electronics Repair. Ciao for now, guys.